Welcome to the presentation on our study, a Usability Evaluation of AFL and libFuzzer with computer science students. Why conduct a study on the usability of fuzzing? Fuzzing is a hot topic in recent years. In science, there's heavy research on it. In the last 2 years, on the top 4 security conferences, over 50 papers were published. Additionally, it is used in large software companies. For example, Google and Microsoft use fuzzing to secure their code. Large fuzzing campaigns like OSS show that fuzzing is a useful tool in finding bugs. However, there are still vulnerabilities discovered every day. One reason for this could be that not every software is tested with a fuzzer. Arguably, fuzzing requires high expertise and not enough experts are present. Therefore, to gain some insights on the usability of fuzzing, we conducted this study. Firstly, we want to provide you some details on our demographics. We started with 47 computer science students with a bachelor degree. 36 participants were male, 8 were female. 3 participants did not disclose their gender. We asked the participants to report their programming experience in years. Their answers lie in a range from 1 to 13, with a median of 7. The participants also self-reported their proficiency in C or C++. The results can be seen in the lower table. We also asked if they used a fuzzer before. Interestingly, 5 participants responded here with yes. As a variety of fuzzers exist, we had to select some of them. We choose AFL and libFuzzer, as both are popular in academia and industry. For example, AFL is commonly used as a benchmark in research papers, and both fuzzers are used in the Google OSS Fuzz project. As target programs, or target libraries in this case, we selected libRoXML and toml C99. They are parsing libraries for XML or Tom's obvious minimal language. We selected both libraries as targets as they are easy to fuzz and we were able to find 0 days in them. They are easy to fuzz because they provide an interface to parse a buffer or a file. We fuzzed each target to find 0-day vulnerabilities in them. Firstly, to make sure that there are bugs that can be found via fuzzing, and secondly, to make sure that there is no information that participants can find on Google. We designed our study within subjects to compensate for the rather low number of participants. We randomized and counterbalanced the assignments to overcome the drawbacks of fatigue and learning effects. For the study, at first, participants had to fill out a pre-questionnaire where they were asked about their demographics and their programming and fuzzing skills. Afterwards, they worked on 2 fuzzing tasks consecutively and were asked to keep a diary about their work during that. Finally, we conducted a about 45-minute long semi-structured interview to get deeper knowledge about their work and their reasoning behind their actions. To reduce the dropout rate, we supported our participants in multiple ways. Firstly, we provided a structure for each task which subdivided each task into 7 steps. Each step is necessary to find a bug with the help of a fuzzer. If the participants used the steps as a guidance, the whole task is less overwhelming for them. Secondly, we implemented a support system. If participants got stuck, they could contact us via email. To encourage participants to figure out their own solution, we did not reply instantly. We replied within the next 24 hours, however, we waited a minimum of 6 hours. Participants that contact us will get up to 2 hints, and if they still don't succeed with the step, they will get help to finish it. To make the solutions provided by our participants comparable, we implemented a scoring system. For each task, a score between 0 and 10 points was possible. Accomplishing each of the 7 necessary steps was rewarded with 1 point. However, if a participant required our help to finish a step, no further points on steps depending on it could be gained. If they found a bug and recognized it as such, another point was given. It was possible to gain 2 additional points by either using a sanitizer or a dictionary or a corpus. These points were given as both technologies drastically improve the quality of a fuzzing campaign. We counted a task as successfully if a bug was found and recognized as such. However, this is possible without reaching 10 points. As our study required handling 0-day vulnerabilities, responsible disclosure was needed. We notified the developers of all programs about all found bugs right after the study ended. The entire experiment was conducted locally and no risk to any live systems was posed. Now to our observations. First, we present some insights into our support ticket system. In this graph, you can see the number of hints we had to give for different steps. AFL is represented in red and libFuzzer in teal. It is clearly visible that libFuzzer users required more help in instrumenting the target program and building the fuzz target. You can also see that the participants struggled with getting the address sanitizer running. This happened with both fuzzers, AFL and libFuzzer. In this table you can see the dropout and success rate for each fuzzer. It is clearly visible that there was a high dropout and low success rate. Of 35 AFL tasks started, only 21 were completed. Those numbers are close to the numbers in the libFuzzer tasks. There, only 21 of 37 started tasks were completed. However, the fuzzers greatly differ in their success rate. While both have 21 completed tasks, 10 tasks with AFL were completed successfully, while this is only true for 5 tasks with libFuzzer. The results in this contingency table only include participants that completed the study, as this allows an easy comparison of the fuzzers. You can clearly see that participants had a higher chance of success by using AFL compared to libFuzzer. If we compare the scores of the 17 participants that finished the study, the differences between AFL and libFuzzer are strong. For those 17 participants, the median score of AFL is 9 and the mean is 8.24, while the median and mean in the case of libFuzzer are 6 and 6.65. Therefore, the difference between means is 1.59. On average, the groups are divided by more than 1.5 points in favor of AFL. Now to our qualitative results and recommendations. Better documentation. The participants struggle with the provided documentation. Additionally, to improving the documentation, we would recommend including a high-level overview, since we saw that many participants did not understand how the steps interact and how they are built on each other. Opt-out sanitizers. While we also observed that it would be beneficial if more participants had used sanitizers, we are not sure whether opt-out sanitizers suggested in earlier work are a good idea. In our larger sample, we saw that many of our participants already struggled with the complexity of the fuzzing process and did not have a good understanding of what was going on. So adding a large number of extra sanitizers and requiring users to opt out could be detrimental to some users. Instead, it might be a better option if fuzzers could guide the users in the use of sanitizers. Build automation. The building and instrumenting with both fuzzers were a major pain point for many of our participants, mostly for libFuzzer, but also for AFL users. A build automation could relieve them from those issues. Error messages. The error messages offered by AFL were generally rated favorably by our participants, while libFuzzer's warnings were considered unhelpful or even non-existent. For example, libFuzzer does not warn participants if the target program was not instrumented. Improving libFuzzer's warning and feedback based on AFL thus is a simple yet effective solution. Metrics of fuzzing runs. The metrics about fuzzing runs currently offered by the fuzzers did not help our participants to judge whether a fuzzer was running well or when it was okay to end a fuzzing run. Developing more helpful explanations for current fuzzing metrics or potentially more user-friendly metrics themselves is an open research question. Crash analysis. Helping users to understand and analyze crashes automatically would also be of substantial help. For our scenario, it would have been very helpful if libFuzzer had been able to recognize that many of the crashes were caused by problems in the fuzz target. However, it would be even better if this was not an issue at all, because the fuzz targets were generated automatically, which leads us to our final point. Fuzz target-less fuzzing. AFL's ability to fuzz an executable without the need to write a fuzz target was of great help, but it only works for programs that receive their controlling input from standard in or files provided by command line arguments. It would be very desirable for fuzzers to be able to automatically fuzz arbitrary functions without much input or fuzzing knowledge required from the user. This is, of course, an open research challenge, but one which is very worthwhile, both from a technical as well from a usability perspective. We hope that our research will lead to increased usability of fuzzers, and thank you for your attention.